Hello everyone and welcome back. My name is Mr. Koval, and in this video we're going to find out how many pounds of coal does it take to heat up 15 liters of water at 1 atmosphere. So let's get into this. So the problem is, how many pounds of coal would you have to burn to generate enough heat to just start to boil 15 liters of water at 1 atmosphere in a kettle that is initially at 25 degrees Celsius? Assuming four things. We're assuming one, that the coal is 95% graphite, so only 95% of it is going to burn. The other 5% is non-combustible impurity, so we have to take that in consideration. We're also going to assume that carbon dioxide is the only carbon-based product formed, so we got to take care of that. And three, that the heat capacity of the kettle is 500 joules per degree Celsius. Now, notice this is heat capacity. Notice the notice the units. It's joules per degree Celsius. If it was specific heat capacity, it would be joules over grams per degree Celsius. But since this is heat capacity, it's going to be just the units are joules over degrees Celsius. This should give you an idea of what you need to do in order to get the energy absorbed by the kettle, right? So I'll talk more about that in a moment. And then finally, the fourth assumption is that 20% of the heat that is generated from the coal is lost to the surroundings. Okay, so what's the first thing we need to do? Well, we need to figure out the total amount of heat we need to be generated by the coal. So the coal itself, that's going to be generated, right? And we are going to have to figure out, well, how much heat is generated from the coal. But remember, we need to get the energy that's given off to the surroundings. We got to get the energy that's absorbed by the kettle. We got to get the energy that is absorbed by the water, the 15 liters of water. Okay, so the first thing we could do is figure out how much heat do we need to get the 15 liters of water to get to the point of just about to boil. So let's look at that. Okay, so the first thing we want to do is calculate the amount of heat needed to boil the water. So we're going to use our Q equals MCAT. So the Q of the water is going to be equal to the mass of the water times the specific heat of the water times the change in temperature of the water. And again, that's going to be equal to the mass of the water times the specific heat of the water. And the change in temperature is always final minus initial. So that's going to be the final temperature of the water minus the initial temperature of the water. So we need to figure out the mass of the water. Well, so let's start with 15 liters. So if we have 15 liters of water, H2O, we're going to want to convert that to mass. We're going to have to use the density of water, which you should know is 1 gram per 1 milliliter at 1 atmosphere and 25 degrees. So we're going to use that as the density of water. So we got to first convert this to milliliters. So 1 liter of water on the bottom, 1,000 milliliters of water on top. Liters cancel out. Now I have milliliters. Now I can use the 1-to-1. So 1 milliliter of water on the bottom and 1 gram of water on top. So milliliters cancel out. Now I have grams, but of course that's going to be 15 times 1,000, which is going to be 15,000 grams of water. So now I have the grams of water. So we can plug that in. I don't need this anymore. That's 15,000 grams. So we got 15,000 1,000 grams. And again, that's going to be the last sig fig, and 15,000 is going to be there because remember, where is it? The number of sig figs in 15 is 2, so we're limited to 2 here. So we're going to multiply this by the specific heat of water, which is 4.186 joules per gram per degree Celsius, multiplied by final temperature, which we want to get it to boiling. So 100 degrees is when water boils at 1 atmosphere of pressure. So that's going to be 100 degrees Celsius for the final temperature, and the initial temperature we're given is at 25 degrees Celsius. So minus 25 degrees Celsius. So now I have everything. Notice grams cancels out. Specific, the degrees Celsius is going to cancel out, and I'm left with joules, which is what I want because I'm calculating the amount of heat absorbed by the 15 liters of water to get it to boil. And so when I multiply all of this together, I get 4,709,000. So 4,709. What was the last part? 250 joules. So this is the amount of heat absorbed by the water just to get the water to boil. But that's not all of the heat that was released by the coal. Remember, some heat is absorbed by the kettle. So now we have to figure out how much heat was absorbed by the kettle. And that's where the heat capacity comes in. We're told that 500 joules of energy is absorbed per degree Celsius. So here we can assume that the temperature change of the kettle is the same as the temperature change of the water. Since the water started at 25 degrees Celsius, and of course the kettle and the water are in contact with each other during this time, it's safe to assume that the kettle started at 25 degrees Celsius, and that also was raised to 100 degrees as well. So what we can do is notice that all we need to do is to get our joules. Remember, joules is the energy unit. So if we can get joules by itself, then we can get the amount of heat that is absorbed by the kettle. Notice that the only other unit we have is degrees Celsius. It's on the bottom. So we would have to multiply this heat capacity by a temperature or a temperature change. So therefore, the Q of the kettle, I'm just going to put K for kettle. The Q of the kettle is going to be equal to the heat capacity. I'm just going to put C for heat capacity of the kettle multiplied by the temperature change of the kettle. So now I can calculate this by writing the Q, the amount of heat absorbed by the kettle is equal to the heat capacity of the kettle, which is 500 joules. 500 joules per degree Celsius, multiplied by the temperature change, and the temperature change is final minus initial. So again, we're going to assume the same here. So 100 degrees. So the final temperature of the kettle is 100 degrees Celsius minus the initial temperature, 25 degrees Celsius. And when I calculate this, notice that degrees Celsius are now going to cancel out when I multiply, leaving me with only a joules, which is a heat unit. And when I multiply this, I get 37,500. So this is going to be 37,500 joules. So this is the amount of heat absorbed by the kettle. This is the amount of heat absorbed by the water. Let's add those together. So when I add these two together, I get So I'm going to add this together just to be clear, and this together. So when I add these two together, I'm going to get 4,074,746,000. Let me double check. 37, yeah. 746,750 joules of energy. Okay, so this is the amount of energy that was absorbed by the kettle plus the amount of energy absorbed by the water. Okay, but we're not done here yet. We were told one of our assumptions is that 20% of the heat that's generated from the coal is lost to the surroundings. So if we're going to calculate the amount of pounds of coal to be burned, well, we got to consider the 20% that was lost, right? So we need to add that to this total here. So let's go ahead and do that. So I don't need this anymore. We're done with this. Okay, we're done with this. Okay, so this is 80% of the heat that was released by the coal, but we want the 100% total, right? Because that 100% total is going to get us to the amount of coal that we actually need to burn. Okay, if we do this amount, if we just leave this amount and continue with this, we're not gonna calculate enough coal. So we know this is 80%. So we want 100%. So 4,746,750 joules of heat absorbed by the kettle and the water. That's 80%, but we want to convert 80% to 100%. So 80% means what? 80% means that out of 100%, let's say out of 100 units of heat, 80 units of that heat is absorbed by the water and the kettle together. So what does that mean? It means that out of 100 units, let's say, since we got joules, we'll say joules. Out of 100 joules of heat produced by the coal, right, only 80 joules is absorbed by the water and the coal. So we want to get the total 100 joules out of that was the total 100% that was released by the coal. So to do that, we can use the percentage as a conversion factor. So this is, let me be clear here. So joules, this is joules absorbed. That's the amount of joules that was absorbed by the kettle and the water. We want the total amount released by the coal. This is the coal released, right? So let's put this as released by the coal. So what we need to do is use that as a conversion. So since this is joules absorbed, I'm going to put the 80 joules absorbed on the bottom. So that's going to be 80 joules of energy absorbed for every 100 joules released by the coal. So I'm going to put 100 joules released. And so now I'm going to use the conversion factor to convert. Joules absorbed is canceled. Joules released is on top. That's what I want. And when I multiply this together, I get, where is it? Let me calculate that. 5 million. So this is going to be 437.5 joules of energy released by the coal. Okay, great. But we haven't finished yet, because what are they asking for? They want to know how many pounds of coal would you have to burn. Okay, so we now know the amount of joules released by the burning of the coal. Now we need to go to our combustion reaction. Okay, so the combustion reaction here, let me erase this, I don't need this anymore. We're told that the coal is 95% carbon, right? Carbon is going to react, the graphite's going to react with oxygen to form carbon dioxide. Carbon dioxide is the only carbon-based substance, so we can write a balanced equation. So we're going to write a formation equation of carbon dioxide. So we're going to have carbon in the form of graphite reacts with O2 to form CO2 gas. So there's our balanced equation. And so we need to know what the heat of reaction is, what the heat of formation of CO2 when you're reacting it with the elements in their standard states. And so if we look that up in our table, we get negative 393.5. So the enthalpy of formation here is equal to negative 393.5 kilojoules. Let me just double check that. Negative 393 kilojoules per mole. Okay, so now that I have this, right, this is per mole of CO2 formed. Of course, we're forming only 1 mole of CO2 in the equation. So now that I have joules here, I can convert joules into the amount of carbon graphite that was needed to get this amount of heat. So now what I can do is I can take this amount here, 5,933,437.5 joules over 1. And now I can use this and the equation and the molar mass of carbon to convert to grams of graphite that was needed to get this, or pounds of graphite. Well, let's convert to pounds since they're asking us for pounds. So let's convert to pounds. So joules, so here I'm going to use this kilojoules per mole, but I need to convert this to joules. So I know that 1,000 joules of energy is equal to 1 kilojoule of energy. So joules cancels out. Now I can use this as a conversion factor. So on the bottom, I'm going to put negative 393. Oh, and by the way, this should be negative 2 because we're talking about the release of heat. So remember, this is the amount of heat absorbed or released. I'm sorry, this is the total amount of heat released by the coal. So we're going to have a negative there. This is negative because, again, this is exothermic. So those negatives are going to cancel out. So this is kilojoules. And then 1 mole of the graphite. So this is going to be C graphite. Okay, so kilojoules cancels out. Now I have moles of carbon, and now I can use the molar mass of carbon. The molar mass of carbon is 12.011. So 1 mole of carbon on the bottom, 12.011 grams of carbon on top. So moles of the carbon cancel out. I got grams, and now I can convert to pounds. And so the relationship between grams and pounds is going to be, let's see, 453.6, 453 point, so 453.5, what is it? 592 grams of carbon, and then that's going to be equal to 1 pound of carbon. And so now grams of carbon cancel out, I got pounds. So now what I can do is I can multiply across the top, divide by the bottom, and I'll get the amount of pounds of carbon in the graphite form that was combusted to produce this amount of joules. And when I do that, I get 0.39927. So that gives me 0.39927 pounds of carbon in the graphite form. Okay, so here, that's the amount of pounds of carbon, but also remember, we can't forget the assumption here that the coal, we don't want pounds of carbon. That's not what they're asking for. They're asking for the pounds of coal. So we need to go from pounds of carbon to pounds of coal, but here they're giving us a percentage. They're telling us that 95% of the coal that's burned is graphite. So again, we can use the percentage as a conversion factor. What does 95% tell us? Again, 95% tells us that out of 100 units of coal, right, in this case pounds, 100 pounds of coal has or is equal to 95 pounds of carbon in the graphite form. Or, I'm sorry, that should be not percent, but pounds, 95 pounds. Okay, so 100 pounds of coal will give us 95 pounds of carbon. We've got the pounds of carbon, so let's convert that back to pounds of coal. So we're going to use this as a conversion factor. So now that I have this, I can now take this, put it over 1, and I'm going to use that as a conversion factor. So I have pounds of carbon on the top. I'm going to put pounds of carbon on the bottom, which is 95 pounds. So 95 pounds of the carbon in the graphite form. And then on the top, we're going to have 100 pounds of coal. So pounds of carbon are going to cancel out. Now I have pounds of coal. And when I calculate that, I get 0.420, 0.420, and that's going to be pounds of coal. Pounds of coal, excuse me. Sorry about that. Pounds of coal. Okay. So that, ladies and gentlemen, is how you do it. We got 0. So it takes 0.420 pounds, less than 1 pound of coal, to generate enough heat, almost 6 million joules of heat, and that's enough to raise the temperature of 15 liters of water from 25 to 100 degrees, but we're losing 20% of that to the environment, and some of that is to the kettle. So I hope this is helpful. If this was helpful, if you enjoyed this video, then by all means, like the video, share the video, hit that like button somewhere over here. Also, do me a favor, subscribe to the channel, help me out. Also, when you do that, click on the notification bell and click all so you'll be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with or a topic you want me to cover, put it down below. Let me know. I would love to do that for you. Thanks for joining me and have a great day.